So today we're going to be talking about Lab 3, which is black hole orbit. And the objectives of this lab were to analyze a star's motion to find the net force on the star by the black hole using Newton's fundamental principle. And as a reminder, Newton's fundamental principle states that F net equals mass times the change in velocity over the change in time, otherwise rewritten as the change in momentum over the change in time. So we're going to observe the effects of net force on the change in momentum and later comment on the difference between F net and dp dt. So later we'll find the mass of the black hole, which was one of the major results of this lab, and we found that the mass of the black hole equals 3.36 times 10 to the 31 kilograms. So we need a few things to start off our computer model, including the star's mass, which was given to us in the initial problem statement. And we're also going to define a time step as 1 Earth day. And lastly, the black hole position, which was also given to us. So next we'll move on to initial velocity, final velocity, the initial and final components of momentum, and then the change in velocity and momentum. So to do this, we take the change in position over the change in time, so the change in the first two positions over the change in their time, to find V initial. And if we take this value and multiply by the star's mass, then we'll get, as we see here, P initial. So if we repeat for V final and then use the same method to find P final, we can then take both and find the difference, V final minus V initial and P final minus P initial. So next we'll move on to utilizing the momentum principle, which again states that F net equals dp over dt, which can be broken down further into its components. So dp dt parallel and dp dt perpendicular. dp dt parallel describes the motion along the parallel direction, and dp dt perpendicular will describe to us the curvature of the orbit. So Fnet describes the sum of all the pushes and pulls, and Fnet is actually what causes the change in momentum, which again we'll comment on in just a moment. So first let's examine the parallel component of momentum. So all of the forces in the parallel direction cause the change in momentum in the parallel direction. Then the change in momentum over change in time in the parallel can then be rewritten as the change in the magnitude of the momentum over time times p hat. And here we see all of this above written in computer language. So next we'll examine the perpendicular direction, and similarly the sum of the forces in the perpendicular direction will equal the change in momentum over time in the perpendicular direction. And since, as we stated earlier, the change in the total momentum over time is just equal to the sum of its components, we can take that, and as we see in the computer code, dp dt perpendicular will equal dp dt minus the parallel component. So taking all of this information and running our computer program, we get this nice orbit where this green arrow represents the direction of the motion or the direction of the momentum, and the red arrow represents the parallel direction, the parallel component of momentum. So we see they're pointing in opposite directions, which implies that the star is slowing down as it orbits the black hole. Then we'll move on to the perpendicular component, which is notified by this blue arrow. And since the blue arrow is pointing towards the center of the kissing circle or the orbit, we take that to mean that this is the direction that the star is turning as it orbits. So lastly, we want to find the mass of the black hole, which we found using the gravitational force. And since that we were told that we could assume that the gravitational force was the only force acting on the star, we could use this and rewrite it as we see here to find the mass, which, as we said earlier, was found to be 3.36 times 10 to the 31st kilograms. So what does it mean? What is the difference between the net force and the change in momentum over time? The change in momentum is a result of the change of the net force. The sum of all the forces in the direction parallel to the direction of motion causes the changes of momentum, or the velocity, in the same direction. And the same is true for the perpendicular effects. And lastly, we wanted to examine what if a new black hole of the same mass, of the same position replaces the old one, but the star's observed motion is the same. We would not be able to tell if the new black hole's mass was different than the old one, since the only force acting on the star is the gravitational force, as we see here. The only terms that we need to utilize to find the mass of the black hole solely rely on the observed motion of the star and the mass of the star. So as we can see, none of these things would affect the change in mass of the black hole.